Okay, hi everyone. Um, so let's go back over Descartes' rule of signs. So here's the idea about this, to make this a little bit more clear. If you have a polynomial of some sort, like p of x equals x to the third power plus 2x squared minus x plus 4, and you wanted to find the roots or solutions of this polynomial, Descartes' rule will help us find what we call the real zeros. Now, remember, when we are solving for a polynomial of this sort, we are looking for the zeros or the x-intercepts to where we're trying to factor this. We're trying to see what this looks like. And that's kind of what we've been trying to do the whole time, but we have all these other methods to kind of help us do that without kind of relating to without going to the graph or looking at Desmos or some kind of instrument, or I should say technology, I should say. So we're trying to see, okay, what if we're going to take this polynomial of degree 3, and remember that the leading coefficient, which is the engine of the train, tells us kind of our leading our kind of our type of graph. So let's do a couple of examples and kind of clarify what the Descartes rule says. So let's look at this example here. F of x equals 4x to the third minus 12x squared minus 5x plus 1. So a couple notes here first, a couple side notes, kind of as you are beginning to do this. So kind of maybe a couple of side notes here. We know that the degree is 3, okay? We know that it's also in order from greatest to smallest. Now that's something that we want to know. And we kind of have an idea because remember, this is the leading term. So the leading term, or I should say degree, and we kind of have a picture in the back of our head, and that's what that picture is going to look like. Something like it's going to kind of go like this. That picture is going to look like that. Remember, that's the way that kind of leading terms, and here your arrows go there, it kind of goes there because you have an odd. Well, that's kind of the picture we want. It's not necessarily going to really look like this with the 0. It might be over here. It might be over here. All right, so here's how we're going to try to approach this. We have our polynomial. We have degree 3. We have kind of an odd shape. We have our leading terms out here. So let's kind of find, well, what do you think is going to happen? I mean, how many times does this function kind of intersect what we call this x-intercepts? How many real roots? How many roots are real roots? Not complex, but real roots. We're trying to find the real roots of this. That's what Descartes' rule is trying to say here. So how do we do that? Well, the first thing we're going to do is that we are going to look at the sign changes. So we're going to take this for a minute here, and we're going to look at the sign changes. So let's go ahead and rewrite this, if you don't mind. Kind of help us out a little bit. Okay, so we're going to say, well, from here to there, there's one sign change. From here to here, there's 0 sign changes. From here to here, there's one sign change. So we can say that the x-axis or x-axis of positive has 2 or no real zeros. So here's what we're trying to show here. This right here, remember, you can put in any number you want. So you can put in 1, 2, 3, 4, 5, 6. You can put in anything up to positive infinity for this guy right there. And what you're trying to do, you're trying to find the roots. You're trying to find the real roots of this. So you're focusing right on here. You're kind of seeing, okay, does this polynomial ever have any positive real zeros? Any positive? And this tells us that our sign changes have 2. And remember how we're going to do this? We always take the number of sign changes. So we take the number of sign changes, take the number of sign changes, and we're going to go 2 minus, n minus 2. N minus 2. So for this one has 2, and then we're going to subtract 2 from that, or 0. So it can intersect twice, or it can be no intersect of the positive axes. Okay, so what about this other axis? Because what about the negatives? What about the negatives? Let's see if maybe by chance this might intersect the negatives at all. Remember, we're trying to get a picture of what's going on with this. So here's what you're going to do. This is kind of right here. This is kind of the positive sign. What I want to do is get the negative sign. So it's kind of like you're plugging a number in. You're plugging in a negative number in. So if I take our function, and I'm just going to kind of do this, if you don't mind, kind of put parentheses where we're going to plug a number in of negative sort. Okay, what we are going to do is plug in, let's say, a negative value. Now that negative value can be anything. That can be -1, -2, -3. But we're trying to focus right here now. We're trying to focus on this side. So on the negatives, because we're trying to see, maybe does the graph intersect the negative side of the axes? That's kind of what this is trying to do. We're trying to see, does this graph intersect the positive or negative side of it? We're trying to get like a picture of it without kind of looking at the whole graph. We're kind of just trying to solve it. So here's what you're going to do. We're going to put in any negative number. So we're going to put in any negative number. Any negative number. That means any below 0. That's what this is about. That's what this is part right there. That says that any negative zero, negative any number. That's kind of focusing on any negative on the axes from negative infinity to 0. We're seeing if this graph might intersect a real number over here. So let's look at this. So we're going to put the negative x in all the places for the x up here. And you kind of need to know how this works, the PIMDOS. So what you're going to do, you're going to kind of look at the exponent, and you're going to say, okay, this has a 3 in it. This is odd. Well, if you multiply this times negative times a negative times a negative, that's still going to be negative. So you're going to write negative 4x to the third. And if you close this one off and you say, okay, well, if you multiply this times 2, or sorry, not times 2, but times this one, negative times a negative, that's still going to be a positive. So that's a positive, but there's also a negative there. That's not going to change. That's still going to be negative x squared. Over here, we have a negative and a negative because we have a power of 1. So that's still going to be negative. And a negative times a negative is going to be a positive. So that's going to be 5x. And then that 1 is just going to still come down there. It doesn't do anything. Now, look at the sign changes as our negative value with our degree changes. So let's look at this. Well, there's nothing there. There is 1 there. There is nothing there. So that means that we have 1 or 0. Remember, this is 1 minus 2. This is 1 minus 2. 1 minus 2 sign changes. So we can say that this graph could intersect or give us a root or a real root at maybe on our graph. Maybe. So that's kind of like what's this trying to accomplish? Now, it's the idea is, well, we have more of a chance of it being positive than negative. So if we look at the graph now and we kind of say, okay, well, we know from our graph of to the third power that this graph is going to kind of do this anyway because we know what the third power does. We know what kind of the leading terms, the leading term degree does. So it's kind of say, well, okay, first off, I want you to look at this. If this is positive x-axis, if this is just the positive x-axis, just the positive x-axis, can looking at this graph, so looking at this graph and also looking at just the positive x-axis, can this graph have two real roots? Can this graph intersect this positive axis twice? The answer is no. So we can kind of say that process of elimination that there is no way that this graph, this cube that side can intersect this twice. It cannot give us two real numbers. It cannot intersect that mean. This means that if we draw this like this, if we kind of draw this, there's no way that this can come back around and intersect that twice. So we can kind of mark that positives out. Well, let's go back down to the negatives. If you put in a negative value, so any negatives here, we can have one or no real answers. But look at this. If our graph looks like this kind of thing with this being a odd number, this has to happen. That means that this graph would have to go upstairs and go like this and intersect somewhere, give us a real answer somewhere at a negative value. So we can maybe have something like x minus some value. Some value, that means a, some value. Or I should go like this, huh? Because that'd be, if we would have set this equal to 0, that'd be the opposite. All right, that's kind of what this is saying. Let's do another one to kind of help us out with this. So kind of do another one here. I'm hoping that this is making a little bit more sense than we had in class. Okay, so let's do something like this. Why don't we do f of x equals 3x squared plus 6x plus 12. All right, a few notes before we start. So a few notes. We're trying to see what type of graph this looks like. We're trying to get a kind of an idea of the factors, the solutions, the kind of it looks like. We know, for example, that it's in order. We also now know it's going to go down. It's a parabola that goes down. Why does it go down? Because the A is negative. So we can say the A is less than 0. So that's a parabola that goes down. We know it's even. We know it's even, so it's going to be a parabola that goes down. Now, if we were to kind of interpret this a little bit more, we can kind of do some more. So let's try to see, since this is quadratic, let's see if we can kind of do a GCF and kind of factor it a little bit because they get harder. This one's an easy one. So let's try a GCF. So we have a GCF. We can take out let's take a -3 out, or we know it goes down. Let's take out a 3. So if we take out a 3, we get negative x squared. If we take out a 3, we have 2x. If we take out a 3, we have 4. Okay, hope that makes sense. Now remember, if you cover up the GCF, and now just focus on this part right here, we can actually do a little bit more. We can actually do a little bit more. And if you do the formula, negative b plus or minus the square root of b squared minus 4ac over 2a. This doesn't factor nicely, so we're going to have to do a little bit of work here. It doesn't factor with the diamond method. So if you kind of put the stuff back in, I'm going to kind of do it fast for you. This should be 48 over 2. You can check my work at home and pause this video if you want to check that work and see if it's correct. Well, that means you're going to have two answers. That means you're going to have two answers. One of the answers is going to be this, 48 over 2, or negative 2 minus the square root of 48 over 2. So these are your two possible answers. Well, that means that, one, if we kind of draw a graph, here's your function, x and y. We kind of understand that it still goes down negative. Here's your roots. And we kind of have something maybe like this, if we were to do these numbers correctly. Well, that's kind of what it looks like. But what if this wasn't a nice quadratic? What if we had an idea, but it wasn't like factorable like this? Because remember, we're looking for the roots. We're looking for the roots. So let's say that we want to test this out. So let's say you have no idea how to solve this. You have no idea what this graph looks like. You might have a little idea, but you want to find out, what side does it intersect on? What's its real roots? Maybe we don't have real roots, but you kind of want a picture of it. So here's what you're going to do. You're going to kind of do the function again. So kind of the same thing like we just did. And you're going to kind of do Descartes sign change. So you're going to start with here. Remember, this right here is positive x-axis. We're trying to see if it hits the positive x-axis at all to kind of give us real roots. So if you put a positive number in here, that's not going to change this. I'm hoping that you understand. That's not going to change our digits. But if you kind of count the sign changes from here to here, that's one sign change. That's no sign change. So how many sign changes are you going to have? You're going to have 1 or 0. Remember, it's how many sign changes you have minus 2. How many sign changes minus 2? So that means this is going to have 1 or nothing. I know you're probably thinking, well, Mr. Boss, that's going to be 1 minus 2, which is negative 1. Well, negative 1 is not, you can't really have negative 1. It has to be 0. So that's going to have 1 or 0 real roots. So this is going to have 1 or 0 x-intercepts. Well, let's focus on the negative part. So if we take our function and now put a negative number in it, so we put any negative number, that's going to be negative x. Now, kind of look at your degrees. That right there is going to still be positive. That's going to be positive. So that's going to be negative 3x squared. That doesn't change. Over here, there's 1 there. That's going to be a negative 6. So that's going to be negative 6x plus 12. Well, how many sign changes now? Well, that's 0 sign change. There is 1 sign change there. Well, if we do this correctly, we know that in minus 2, this one has 1 or 0 sign changes, or x-intercepts. Well, 1 or 0. Now, I want you to go back to the graph. This is our proof right here. This is what we figured out from our information because this was a nice quadratic. I want you to think about this now. On this side of the axes of all positive, how many times did we say that it's going to intersect? We have 1 or 0. look at right here. We have one intersection. So boom. Now let's go to the negative. If we put it in any negative number, remember we had 1 or 0? Boom. That right there shows us that these graphs are, this is going to intersect once on each side. This is kind of what's going on. This kind of gives you an idea about, hey, how does this Descartes part work in all this? All right, I want to do one more and kind of make it a little bit of a tough one. And we're not going to graph it. There's no way. So let's try a more complicated one. There we go. So we're going to try this complicated one. And this is the last one we're going to do. So kind of do this here. And let's make this one a little bit more complicated. So try to make this darker for you. So we have x equals, let's do 9x to the 6 minus 3x to the 5th plus 33x to the 4th minus 11x to the 3rd plus 18x squared minus 6x and plus 1. All right. There is no way that you would, this would be hard. We're trying to graph this, or we're trying to find the solution. Remember, our goal is to try to solve. We're trying to find the x-intercepts. There's no way. There's a lot here. You have 6 power. So we have to kind of have a picture. So here's kind of a note. Here's what we knew. Here's what we have. We know that, one, the degree is 6. So remember, the degree is positive. So if the degree is positive and the leading term is positive, that we're going to have a parabola that goes like this, right? Because the degree is even and it's positive a. That means it's going to be going to the end behavior. So the end behavior is going to go back up. Okay. Well, is that really it? Yeah, that's pretty much all you really can do. But the next thing is this in descending order: 6, 5, 4, 3, 2, 1. That's it. So that's an order. So order checked. All right. Well, that's really it. We can't really do a whole lot. We kind of know what the end behavior looked like. So let's see. So we're going to see how many real roots are there. How many real roots are there? How many solutions? How many x-intercepts possibly? Okay, so here's the idea with this. So we're going to put down the same function. I like to always do this to kind of help you look at this. It's a long one, I know. All right, so let's use Descartes' sign. Remember, this is positive, so we're doing the positive first. We're doing the positive x-axis. So you can put in any number you want, but we're going to put an x. Let's count how many sign changes. Let's count how many sign changes we have. Well, here's positive. We have 1. We have 2. We have 3. We have 4. We have 5. We have 6. So just make sure 1, here to here, 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 1. So we have 1, 2, 3, 4, 5, 6. So we have 6 sign changes. So that must mean we have n minus 2 sign changes. So here's what you're going to do. You have 6 or 4 or 2 or 0. Now you're probably thinking, where did I get those? Remember, we're taking this sign changes and subtracting 2. We're kind of like doing even. So here's what you're doing. So you can have 6, subtract 2, you could have 4. Subtract 2, we can have 2. Subtract 2, we can have 0. So that means this thing can have 6 roots, 4 roots, 2 roots, or no roots at all on the x-axis. So let's try the other axes. So if we take this and put a negative in it, and kind of go like this and put a negative to the 6th power, negative x to the 5th power, 33 negative x to the 4th power minus x to the 3rd power. Hopefully I have room to write all this. 18x squared minus 6x negative x plus 1. Count how many sign changes we have. Well, we know that this is even, so that's going to just be 9x squared. We know that this is odd, so that's going to be negative, so that's going to be positive 3x to the 5th. We know that this is even, so that's going to be even, or positive, so that's going to be 33x to the 4th. We know that this is odd, so that's going to be negative times the negative. We know that this is squared, so that's just 18x squared. We know that this is even, or sorry, odd, so that's going to be negative times the negative is a positive, and then plus 1. All right, now let's count how many sign changes we have. Well, we have no, 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 and we have no. Make sure we did that right, just with the x's. Okay, did that right? That means that we have no negative x x-intercepts. That's kind of nice. We have no negative x-intercepts. So what if we have a picture here? Now this is kind of hard to kind of visualize a little bit. Here's your x. According to this, there is nothing going to be over here. There is nothing over there, which is kind of nice. Okay, so remember we can have 6, 4, 2, or 0. Well, if you look at the in behavior, the in behavior is going to be kind of look like this, right? In behavior is going to be positive, positive. Well, that thing can kind of maybe do 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6. It might look like that. It might. We don't know. Because we're trying to take a guess. But we know it's all going to be positive. We all know it's going to be positive though. It could be 4. So let me kind of draw another one over here for you. So here's that. It can kind of go positive. So maybe it can go 1, 2, 3, 4. So we kind of have a feeling of where it might the x-intercepts might be. That's kind of what this whole thing is about. This Descartes sign change is kind of saying how many possible x-intercepts do we have, and that kind of tells us maybe on one side of the graph or the other side of the graph. And it's very hard. This one was nice because it gave us nothing on the negative part. It was kind of nice because there's nothing here. So that means that there is nothing over here on the negative. So it's all going to be the positive. And this is a big possibility there. Okay, so that's kind of the whole idea of sign change. All right, I'm hoping that this helped a lot. And just remember that you just got to keep practicing, and hopefully that should be fine for you. All right, awesome. Thank you.